I'm Dylan Craig, and on behalf of the Earth2Moon team, it is my honor to present to you our lunar transfer vehicle, a culmination of dedication, innovation, and a shared vision of returning humans to the moon. As we embarked on our journey in our senior design course, we were tasked with a monumental challenge to design and create a vehicle capable of delivering astronauts to the lunar surface, a feat not accomplished since the 1970s, a time that predates the birth of many in our team. Our mission was clear: to craft a vehicle capable of transporting 4 astronauts to a 200-kilometer orbit and then safely to the moon's surface. This vehicle must also be able to rendezvous with NASA's Lunar Gateway, not expected to launch until 2025. In approaching this challenge, we adopted a philosophy centered on sustainability, reusability, and above all, safety. Recognizing the significance of this mission and the scrutiny it will face, safety became our paramount concern. Therefore, we have meticulously designed every aspect of our vehicle with safety at the forefront of our minds. Our choice of the Falcon Heavy as our launch vehicle underscores our commitment to proven technology and reusability. With its track record of success, the Falcon Heavy has provides a reliable means of launching our vehicle into orbit, setting the stage for the lunar journey. The transfer vehicle is equipped with innovative features and built-in safety margins to ensure a successful mission. Leveraging similar systems and optimizing cost efficiency, we've designed a vehicle capable of navigating the challenges of lunar exploration while prioritizing the safety and well-being of our crew. Outlining our concept of operations for a groundbreaking mission. In 2038, we envision a Falcon Heavy launch from Cape Canaveral, setting our trajectory towards the moon. After shedding the first stage, a routine step in the Falcon Heavy's launches, we will maneuver into low Earth orbit before executing translunar injection burns to rendezvous with the Lunar Gateway. Once at the gateway, our crew will conduct tests and operations, deploying the lunar relay vehicle from the historic landing on the lunar surface. This momentous occasion will mark the first human presence on the moon in over half a century, an achievement made possible by our collective efforts and dedication. Following their mission on the lunar surface, the crew will return to the gateway, where they will perform another burn to begin their journey back to Earth. In conclusion, our lunar transfer vehicle represents not only a technological marvel, but a testament of the resilience and determination of the human spirit.
For the budget of our program, it was originally slated to be 20% of the yearly NASA budget and was originally based on the fiscal year 2022 inflation rates, which was approximately 6%. This gave us a total allotment for our program of $119 billion. And our highest yearly allotment was $12 billion almost, which can be shown in the figure to the right. However, after using the Advanced Mission Cost Model developed by NASA for a transfer vehicle, it ended up yielding a total program expenditure of $22.7 billion, which is well within budget limits and is not expected to either get close or exceed the budget. For our vehicle overview, the fly sheet can be shown in the figure to the right. The vehicle will have the ability to relay to the lunar surface, back up to orbiting space station, and back down again, and be able to repeat this relay as many times as is needed. It will also have the capability to accommodate up to 4 astronauts with an additional payload. The specifications of the craft can also be seen, where the delta V designed around is 2,900 meters per second, with a dry mass of 9,649 kilograms, a wet mass of 21,307 kilograms, with a thrust to weight ratio that is high at 3.2 to 1. And for the propulsion, it has an RL-10C engine developed by Aerojet Rocketdyne with only one engine at a thrust of 110 kilonewtons and a specific impulse of about 465.6 seconds. The timeline of our program can be shown in the figure to the right, where the totality of the project is expected to run from 2024 to 2040. The overall project is expected to run from 2024 to 2039, with the various design phases listed below, with the flight tests supposing to be in 2037 or early 2038, and revisions happening afterwards.
Now, delving into the intricate details of our mission, we explore the orbital mechanics and the trajectory of the translunar injection. Our journey from low Earth orbit to rendezvous with the lunar gateway involves a series of precise maneuvers and calculations. To achieve this rendezvous, we will execute two burns. The first burn with a delta V of 1.35 kilometers per second, which will last a duration of 26.5 seconds. This initial burn sets our trajectory towards the lunar gateway. Following this, we will perform an intercept burn with a delta V of 2.14 kilometers per second, lasting 22.5 seconds, adjusting our path to meet and match the speed of the lunar gateway in order to dock. Simulating these maneuvers required meticulous planning and adherence to specific stipulations. Optimizing the trajectory involved intercepting the lunar gateway at the closest point, minimizing inclination changes, and maximizing efficiency. This narrow window of opportunity necessitates the precise timing for launch, testing, and all mission operations. Furthermore, the spacecraft's attitude control and thrust management were critical factors in executing these maneuvers. Our simulation accounted for the specific impulse and mass flow rate to accurately model the thrust profile required for each burn. It's essential to note that while our simulation provides valuable insights, real-world conditions may introduce additional complexities and variables. Therefore, through testing and validation are essential to ensure the success of our mission.
For the Earth-to-Moon Lunar Ascent Vehicle, it will be a single stage-to-orbit vehicle. It will have a required propellant mass of approximately 8,300 kilograms of liquid oxygen and almost 1,400 kilograms of liquid hydrogen, given the respective fuel ratio of 5.88. It will also have the respective tank volumes due to densities, with liquid oxygen being the lower volume of 7.646 meters cubed and hydrogen being 20.927 meters cubed. The dry mass of the vehicle is less than half of the wet mass at approximately 9,600 kilograms, with the wet mass being 21,300 kilograms. Both of the mass fractions, inert and payload, are well within the expected ranges, with the inert mass fraction being 0.4766 and the payload mass fraction being 0.0939. The cargo module of the craft will be responsible for housing any and all cargo that will be used in mission. This is included but not limited to life support items like food and water and other equipment that will be need to relay to the lunar surface. It is designed to be accessed from both the capsule and outside in order to maximize accessibility. Also, it is designed to hold up to 1,000 kilograms using the supports featured in the figure to the right. However, since the astronauts will likely make up a significant portion of this payload, it will realistically be carrying something like 600 kilograms, but if there is a mission where there are fewer astronauts using the craft, it can hold higher payloads. The loading and unloading system will use a winch and belay system. This is shown in the figure to the right, where the winch cable is hooked up to a belay that is connected to the aft cargo hatch. The aft cargo hatch will open up outside, expanding the belay and allowing the cargo to be transported to and from the lunar surface. It can also be directly accessed from the capsule, as previously discussed, making cargo loading from the lunar gateway to the launch vehicle as efficient as possible. The lunar capsule for the Earth-to-Moon vehicle will be responsible for mainly for the safety of the astronauts. It will also have to have some room for housing the RCS system and the life support. While it must house all of these components, it must balance these proportionally since the astronauts will need a significant amount of room, well as the components. It will also be the sole module responsible for docking. The capabilities of the lunar capsule are primarily shown in the figure to the right, featuring the IDA-1 docking adapter, which will be able to interface with the Lunar Gateway system after using its retractable nose cone. Also, the RCS thruster locations are shown, and these were found to be optimal as putting RCS thrusters on the capsule at the top of the craft were found to affect the moment on the craft the highest, giving the most efficient RCS system use. The component storage module is also shown, which is where the hydrazine and liquid oxygen will be used for those thrusters. It also will have adequate room for the components like a sensor bay and electronic systems, with the crew compartment giving a plentiful amount of space. It will also hold approximately 1,600 kilograms of RCS propellant and will have 6 independently mounted thrusters.
Hi everyone, today I will explore the Environmental Control and Life Support System, or CLSS, which plays a critical role in maintaining life-supporting conditions for astronauts aboard spacecraft. ECLSS system managing atmospheric conditions, water supply, and waste, ensuring that space environments are survivable and comfortable. In space, replicating Earth-like atmospheric conditions is crucial. EC ECLSS maintains an ambient pressure of 14.7 psi, a mix of 79% nitrogen and 21% oxygen, a comfortable temperature of 22 degrees Celsius, and about 60% humidity. These conditions are vital as astronauts consume 0.84 kilogram of oxygen daily and produce significant amount of CO2. Next is oxygen generation. Uh, uh, while Now let's talk about how we generate oxygen. While short missions may use oxygen tanks, long-term missions rely on regenerative sources like electrolysis oxygen generators. This system splits water into oxygen and hydrogen, providing a sustainable oxygen supply crucial for lunar mission. So let's move to the next slide. CO2 removal system. Removing carbon dioxide is just as important as providing oxygen. We compare two systems, non-generative system using lithium and regenerative system using polymerized, which can be reused and also help control humidity. The next is trace contaminant. Trace contaminants from human metabolism and spacecraft materials must be removed to protect crew health. We use combination of active carbon filters, chemicant bits, and catalytic burner to ensure that air remains safe and clean. Now let's talk about the water. Water is a critical resource in space, used not just for drinking but also for hygiene, food preparation, and as contingency reserve. Managing these resources efficiency is cornerstone of ECLCC. The next is water is the water. Water is Now let's talk about the water. Water is a critical resource Water is a critical resource in space. Now let's move to water supply and generation. Water is a critical resource in space, used not just for drinking but also for hygiene, for food preparation, and now let's move to water supply and regeneration. Water is a critical resource in space, used not just for drinking but also for hygiene, food preparation, and as con- contingency reserve. Managing this resource effectively is cornerstone of ECLSS functionality. Now let's talk about food. Nutrition is key in space. Our systems proved astronauts with both nutrition natural from foods and thermostabilized food, which are selected for their nutritional value, shelf life, and the psychology. Now let's move to nutrition is uh, Now let's talk about food. Nutrition is key in space. Our system proved astronauts with both natural from foods and thermostabilized foods, which are selected for their nu- nutritional value, shelf life, and the psychological benefits. They offer the crew moral and satisfaction. And now let's move to thermal regulation. Managing the extreme temperature of space is challenging. Our spacecraft use multi-layer insulation and an active thermal control system to protect against cold, the cold of space and the heat from solar radiation and onboard systems. Finally, finally, discuss. Let's discuss life aboard the spacecraft. Astronauts sleep individually. Finally, let's let's discuss life aboard the spacecraft. Astronauts sleep in individually spots that offer comfort and privacy. During spacewalks, they wear specific design EF EV. Finally, let's discuss life aboard the spacecraft. Astronauts sleep in individually pods that offer comfortable and privacy. During spacewalk, they wear specifically designed EVA suits that provide life support, temperature control, and protection from space hazards.
Let's delve into the propulsion system, essential for the success and safety of our mission. In selecting the propulsion system for our lunar descent vehicle, extensive research and analysis via trade study were conducted to identify the optimal engine for the task at hand. All the engines you can see were put under close consideration and boast impressive statistics and are highly optimized for vacuum performance. Parameters such as the high expansion ratios and specific impulse signify their efficiency in space operations. However, it's important to note that each engine is designed with unique objectives in mind. Our primary consideration extended beyond the ISP and the expansion ratio and the thrust. Throttle ability and technology readiness level were crucial factors in our evaluation process. Throttle ability is particularly significant as it allows us to modulate engine thrust, ensuring that our crew experiences safe acceleration levels not exceeding 2 Gs of force. After careful analysis, the RL-10C2 vacuum engine from Pratt & Whitney emerged as the clear choice for our mission. With the highest specific impulse among engines considered, the RL-10C2 promises to significantly reduce weight and overall cost, thanks to its exceptional efficiency. Also worth mentioning is that it has been proven to throttle from 104% to 18% of maximum thrust. The rocket engine RL-10C2 that we're using is powered by liquid oxygen and liquid hydrogen. We aim to strike a delicate balance between those parameters. The RL-10C2 is powered by liquid oxygen and liquid hydrogen. In our mission, we aim to strike a delicate balance between performance and utilization. In light of this, one key optimization strategy we're implementing revolves around the oxidizer to fuel ratio. By fine-tuning this, we not only enhance the overall efficiency and effectiveness of the engine, but also aim to optimize fuel consumption. The optimization directly impacts performance metrics and plays a crucial role in managing weight constraints of our landing vehicle. As you can see, the liquid hydrogen and liquid oxygen flowing through the engine, the parameters are seen on the screen, such as mole fraction, mass fraction, and the engine process. We've found through many analysis that 5.88 fuel to oxidizer ratio is the optimum ratio, yet we expect 96% of maximum performance. The RL-10C2 engine operates on a gas-generated expander cycle. Liquid hydrogen and liquid oxygen are pumped into the combustion chamber, where the liquid hydrogen cools the engine and drives the turbine. Excess gas generated is expelled through the nozzle to produce thrust. Notably, this engine does not require a pre-burner. Instead, the heat in the combustion chamber vaporizes the fuel, enhancing simplicity and reliability. Moving towards thrust vector control, we aim to optimize the gimbaling for precise maneuverability. A brushless DC torque motor will power the gimbal mechanism, allowing for controlled movement of the engine. Position sensors will ensure accurate alignment, providing crucial feedback to the crew during ascent. Additionally, incorporating deflection arcs and fans will enable rotation up to 8 degrees, granting the engine the ideal range of motion to execute our mission objectives.
For the auxiliary propulsion of the craft, the RCS system that we chose was the Apollo R4D system. We chose this because it has mission heritage, and we did a weighted study that also featured the SpaceX Draco thruster system, and it was found that the Apollo R4D had a much more efficient thrust and ISP when compared to the Draco thrusters. The Apollo R4D thrusters use a combination of MMH, or better known as hydrazine, and liquid oxygen in the form of nitrogen tetroxide. This will be housed in the capsule, which was discussed in an earlier section, and the layout of the thrusters can be seen in the figure to the right. The thruster layout will allow full control over the fine-tuned adjustments of the craft when in ascent or descent. The liquid main engine control will be dictated by a full authority digital engine control system. This means it has full authority over the navigational control subsystems. It will be able to pick these parameters up and monitor them in real time, and if it detects any faults, it will be able to correct them autonomously. These parameters include, but aren't limited to, the engine gimbal, throttling, and other parameters. A diagram of the placement and how this will work is shown to the right, where it can also control the actuators and other sensors. Liquid propellant tank pressurization was chosen as helium. It was chosen because it is an inert gas, meaning it will not react with the liquid oxygen or the liquid hydrogen, which is incredibly reactive, and it is also lightweight. Since it is lightweight and we were trying to save as much weight as possible for reusability, it was heavily favored over other pressurization systems. The tanks themselves will also include a vacuum pump and leak detection system for safety. For the structural design of the craft, the first component we analyzed was the center of gravity. The center of gravity with wet mass was calculated at 5.2 meters, and the wet mass center of gravity is pictured in the figure to the right, along with the overall systems. As can be seen, the vehicle is segmented into three main components: the capsule, the cargo module, and the fuel tank housing, with the RL-10C engine at the bottom. The LOX tank, hydrogen tanks, and helium tanks are also pictured, with the capsule having the ISS docking adapter. The center of gravity is also located near the geometric center of the craft, which is to be expected for a stable rocket. And since the center of gravity increases as the dry mass is reached, it will move upwards relative to the vehicle, which will be accounted for in the avionics. The type of structures that were chosen for each part of the craft differed greatly. For the main vehicle body, orthogrid was chosen due to its ability to save weight, while the normal stringer and rib placement theory is what is traditionally chosen for launch vehicles. We saw that orthogrid was able to save up to 500 kilograms of weight, giving us a huge advantage, especially when trying to design a reusable vehicle. The propellant tanks will use a standard strut placement system, a part of which can be seen in the figure to the right with the tanks, which will connect to various points to reinforce the tanks. The primary material used was a titanium alloy, aluminum 2024 T3, and it was chosen because of its mission provenness, and it pertains to the vehicle's body, cargo module, capsule, and propellant tanks. It also boasts a low density, further allowing us to save weight, making our thrust module more efficient. The only time this differed was with the engine mount, where we chose a titanium aluminum alloy at an aged grade. It was chosen because it has an incredibly high tensile strength, and since this is the part of the craft where the thrust loading will be the highest, we felt that it was smarter to go with something with such a high strength, even though a little bit of mass had to be increased. These materials were also chosen as the result of a trade study, and the trade study was completely comprised of materials with mission heritage. These materials included aluminum 6061, stainless steel 304, pure titanium, and aluminum 2023, along with the ones that were already chosen. For the structural load calculations, the first structural load that was analyzed was that of the body. Now, the vehicle was tested the most in terms of the body at 2 points, when it lands and when it is under thrust compressive loading. The thrust compressive loading is when the thrust of the craft and the weight of the vehicle itself is compressed upon itself due to the gravity of the moon. However, the moon's gravity is not incredibly high, so there was reason that the margin of safety was going to be in accordance. Now, since it was an orthogrid skin, the equation used was in accordance with NASA research, which is shown in the center. This is sigma crit is equal to the stiffening factor along with the Poisson's ratio, elastic modulus, the thickness, and the radius. For the force of landing, it was calculated to have a maximum stress point of 7.956 megapascals. And after using a effective thickness of 11 millimeters, it gave us a safety margin of 1.55, which is the desired safety margin for the body. Now for the landing force, it was significantly weaker than the compressive thrust loading force, so it wasn't as worried about. But it was considered to be an impulse since it was assumed to be landing at about 1.8 meters per second, which is a nominal landing speed. This resulted in a minimum thickness of 3.84 millimeters to resist this, calculated mass of 21,000 kilograms, and gave us a margin of safety of 6.78. For the prop tanks, a different approach was taken since they were pressure vessels. These were using the hydrostatic equations of absolute pressure, which are pictured below. This accounts for the atmospheric pressure of the Earth, and it was analyzed on Earth because that was the highest point of strain that the tanks would be tested at, along with the geographic strain of the pressure given by its density and gravity, and then the initial pressure, which is shown to the right. All of these initial pressures are NASA standard, with hydrogen having an initial pressure of 228 kilopascals, LOX having 450 kilopascals, hydrazine at 179 kilopascals, and helium at 301 kilopascals. After finding these initial pressures and putting them through the absolute pressure equation, this was used in the critical stress equations, which were shown below, where sigma theta is the hoop stress, which is the higher of the two, and sigma axial being the longitudinal stress, which is the more vertical component. Now, after analyzing these in MATLAB, we put in a parameter for a minimum margin of safety of 1.75. All of the thicknesses of the tanks were designed around this thickness, or margin of safety. This resulted in the hydrogen tank having a thickness of 4.6 millimeters, LOX having a thickness of 11 millimeters, hydrogen having a thickness of 1 millimeter, and helium having a thickness of 2.867 millimeters. It should be noted that the final thicknesses of the tanks were all thicker than these calculations. This was mainly due to the fact that the hydrazine thickness felt a little low, so we felt that we needed to increase its thickness to account for any vibrational stresses. After these loadings were found, they were put into finite element analysis. This was executed through SolidWorks, which has a very accurate analysis. The first component analyzed was the body, where, as can be seen, the thrust was applied to the bottom and the force due to gravity applied to the body itself. This resulted in a maximum von Mises stress of about 2.7 megapascals and a maximum displacement of 0.2 millimeters. For the LOX tank, it was similarly done, except it was treated as a pressure vessel, so the pressure was applied inside of the tank in SolidWorks. This gave us a maximum von Mises strength of 0.14 megapascals and a maximum displacement of 1.5 times 10 to the negative fifth millimeters, which is well within respected diameters. For the fuel tanks, it was a maximum displacement of 0.4 millimeters and a maximum von Mises stress of 33 megapascals, which are still a respectable margin. As can be seen in the figure below, especially with the hydrogen tank, all of them were well within safe limits. For the aerodynamic section of the craft, there is no atmosphere on the moon, so the aerodynamics were not heavily considered. And in terms of aerodynamics on Earth, the Falcon Heavy will be handling that. And since it is within the fairings, and the fairings are designed to deliver as little stress as possible to the payload, it is not a point of contention. For the electrical protection of the craft, there is no lightning on the moon, so that was one factor that did not have to be considered. Now, as for the extraneous plasma charges, the electrical module will use a Faraday cage. The basic operation of a Faraday cage is shown in the figure to the right, where it protects the contents inside of the Faraday cage from plasma and other electronic charges to keep the charge inside constant. This prevents all sorts of electronic damages and also has the bonus of being able to prevent radioactive interference. For the avionics guidance, navigation, and control, avionics pertains to all parts on the craft relating to electric systems and is arguably the most essential component when in terms of successful vehicle delivery. This is split into three main components, the first one being guidance, which is responsible for the control of the vehicle during trajectory changes like acceleration, both negative and positive, and Hohmann transfers. The navigation module will keep track of vehicle location at all times, while also being able to relay that data back to mission control. And the control module is what fully relays and logs data and handles all sorts of telemetry. For our components, the avionics will be composed of a star tracker and Deer camera for position tracking as a part of guidance, and the main navigation system as well. This is due to the fact that GPS will not be available during lunar operations as it is unobtainable on the moon currently. The spacecraft dynamic controls will be responsible for all of the guidance parameters and orbital maneuvers, namely Hohmann transfers and lunar ascent and descent. The star tracker and a Deer sensor can be seen pictured to the right, where the star tracker uses the position of celestial bodies, stars, in reference to the vehicle and how they change over time to ascertain the position of the vehicle. This is based on a 3-coordinate system, X, Y, and Z, and it is constantly updating these coordinates. However, we decided to be redundant in our position sensing and also included a nadir sensor. A nadir sensor is essential because whenever the star tracker is unable to obtain the location of the stars that it was originally tracking, it will be able to track the surface of the moon and be able to keep the vehicle within constant parameters. Both of these were chosen because they are incredibly accurate and comparative to the battery, they have a very low power consumption. However, the only downside is that the nadir sensor is pretty much for local applications as it requires a surface to analyze. But it is, again, used in redundancy. For the more specific parameters, the inertial measurement unit, or IMU, will be able to obtain the real-time parameters of the vehicle. This includes, but is not limited to, specific gravity, angular rates, and other values pertaining to the operation of the craft. Another essential avionics component is the ADI docking sensors. The docking sensor will be the primary component in charge of the autonomous docking process, as it will be able to relay the position of the craft relative to the Lunar Gateway, or ISS, and be able to update the speed and have full authority over it in order to ensure a safe and successful docking.
The design of our lunar landing systems has undergone extensive testing to ensure reliability and safety. This assurance has led to configuration of the landing gear, which closely resembles past successful landings. Among the components undergoing rigorous testing, the landing pads and legs of the system bear the greatest stress. For these critical components, we've selected materials with a proven track record in lunar landings, aluminum alloy 6061 with titanium bearings. This choice ensures the durability and reliability in the harsh lunar environment. Drawing inspiration from NASA's Apollo missions, we have adopted a cantilever-type landing gear configuration. Each leg consists of one of two primary struts, two secondary struts, one footpad, one uplock assembly, two deployment mechanisms, two downlock assemblies, one cross truss assembly, and one lunar surface sensing probe. Not pictured are the uplock, downlock, and deployment mechanisms used to stow the landing gear during flight and to deploy it and lock it in place. The landing gear assemblies are designed to accommodate surface irregularities, including protrusions, depressions, and surface sinkage up to 60 centimeters. The effective slope at touchdown point should not exceed 12 degrees derived from these careful considerations. Additionally, the landing pads can pivot to accept minor irregularities of the surface with a minimum bearing capacity of 12 psi. The landing speed envelope for the gear assemblies ranges from 7 feet per second vertical to a maximum horizontal speed of 4 feet per second. These specifications ensure a safe landing controlled on the environment. Also from past landings, the fastest lunar descent recorded was 6.33 meters per second. This goes into our analysis as we are over analyzing and accounting for more stress than a 6.33 meters per second descent would be. Pairing this with the lunar gravity and the 4 legs to achieve balance, we believe that these legs will safely pave the way for a successful exploration. Despite the low gravitational force on the lunar body and the absence of an atmosphere, there are still losses that must be accounted for to accurately determine the energy required for a successful maneuver. To quantify the losses due to the moon's gravitational force, the delta V grav loss equation can be seen below. This calculation yields an additional 1.35 kilometers a second for the necessary missions delta V. Another form of losses considered in our design is steering losses, which occur when a vehicle's thrust vector is not parallel with its velocity vector. Estimating these losses is challenging prior to launch, so we looked into similar vehicles such as Saturn V third stage to provide an accurate estimation. Assuming these losses will be less than 100 meters per second, although not a direct comparison, this estimation provides a valuable benchmark for our vehicle. Additionally, propulsion systems or thrust losses can occur when a vehicle's design does not effectively utilize the exhaust velocity or specific impulse. Fortunately, our vacuum optimized design does not capitalize on these values, minimizing these losses. Drag losses are not a concern for lunar missions as the moon lacks its own atmosphere, while drag and thrust losses are factors in Earth launches, particularly with Falcon Heavy boosters. They are not significant during orbit maneuvers and lunar stages of the mission. Taking all these factors into consideration, the lunar module design delta V is increased by 25% to 6.3 kilometers per second.
Now I will explore the essential space communications. SCAN includes the Near Space Network and Tracking and Data Relay Satellite System, ensuring continuous communication during key mission phases. Our system aligns with CCSDS standards to transmit data efficiently, supporting quick troubleshooting. We use robust encoding to prevent data loss, ensuring our system maintain connectivity. Now I will explore essential space communications. SCAN includes the Near Space Network and Tracking Data Relay Satellite System, ensuring continuous communication during key mission phases. Our system aligns with CCSDS standards to transmit data efficiently, supporting quick troubleshooting. We use robust encoding to prevent data loss, ensuring our system maintain connectivity in all conditions. Now let's move to the next slide, communication function. Space communication function operate through three primary functions: uplink, downlink, crosslink. Uplink receive commands from Earth, downlink sends data back to Earth, and crosslink allows for data exchange between satellites in orbit. Finally, frequency management. Our communication systems operate within wide range frequency from 30 MHz to 60 MHz. Lower frequency bands often face contingency licensing challenges, while higher frequency offer better performance but come with increased loss factors.
For the vehicle health monitoring for the Earth-to-Moon lunar ascent vehicle, it will be responsible for analyzing the state of the craft to report back to mission control and the crew for corrections. Some essential functions of the system include the development of flight computer algorithms, consolidation and verification of sensor data, the modeling of functional faults, the radiation detection system, environmental control system monitoring, and structural integrity sensors, and along with energy system analysis. For the flight termination system, it will aim to cease the operation of the vehicle in the most efficient way possible. This will mainly involve using charges that are strategically placed along the propellant tanks, fuel lines, and engine to disable the craft, with a concept that as follows. First, the charges will detonate, which will leave the propellant tanks, engine interior, and fuel lines exposed to the vacuum. Once every place where there can possibly be fuel is exposed to vacuum, all of it will combust, which will successfully destroy and disable the craft. However, while it must also disable the craft, it must do so without causing any damage to external entities. This mainly pertains to the surface of the moon, as it is highly sensitive to vibrations, and any other structures that may be nearby. The operation for the termination control unit is shown in the figure to the right, which shows that there is an embedded failsafe system in case it does not detect and execute on the normal flight termination parameters. For the flight test plan, it will consist of a series of tests to ensure not only vehicle safety but successful vehicle operation, and it is a critical part of ensuring that there is a mission success. For this phase, some of the tests include vibrations tests and structural integrity testing, along with vacuum simulations and avionics and sensor operations testing. There will also be a test conducted on the health monitoring system verification, and it will also be static fire or dry runs of the craft. A more detailed outline of our flight plan is shown below, with the cryogenic proof test, which will occur for the propellant tanks, verifying that they are able to cryogenically operate. This will occur in late 2029 or to early 2030. The overall structural testing phase of the vehicle, which includes some of the tests mentioned earlier, is scheduled to occur between 2027 and 2030. The static fire tests which is testing the engine before it is mated with the rocket, is to be conducted between 2028 and 2031. The flight termination tests, which consist of feeding the flight termination system data where it would reasonably terminate flight and simulate conditions causing it to fire, will occur between 2028 and 2031. The wet dress rehearsal is scheduled to be late 2034 or early 2035, close to the test flight, where it is rolled out to the test pad and launch conditions are replicated. The actual test flight will occur in approximately 2037 to 2038. And that draws a conclusion on our Earth-to-Moon lunar ascent vehicle. If you have any questions, comments, or concerns, please feel free to reach out, and thank you for your time.